OALabs is an awesome technical YouTube channel about malware reverse engineering and analysis, and I reached out to them and asked if they would be interested in making a guest video for LiveOverflow. They cover topics I have basically never covered here and I also don't really know much about. So I'm super excited to present you a video from them here. In this video, they will walk us through an example obfuscated malware and explain how you can unpack it in order to get to the real malware executable. And along the way, they will explain a lot about Windows, how typical malware operates, and also how to use tools like x64debug, IDA, or PEBear. One thing, for example, I had no clue about at all was the command attrib to reveal hidden files. So why don't you give them a chance and see what you can learn from this video?
Hi folks, and welcome to Open Analysis Live, or LiveOverflow, or one of the lives, all the lives. I'm Sergey.
I'm Sean.
And you might recognize us from our channel over at OALabs, where we do a lot of videos on malware analysis techniques, different tips and tricks and stuff like that to help analyze malware. So today what I want to talk about is a type of unpacking technique that you would use to unpack malware that does self-injection. So self-injection is not as common as remote process injection. So probably most of the crimeware, criminal malware that's packed today uses process injection, where they spawn a second process, suspended, and then they hollow out the code that's already in the process and inject their own code into it, or they inject like a new thread with a DLL or something like that into the second process, and then it looks like there's a benign process running, but really inside is their malware. So that's the most common method of injection. But we also see some malware that still uses self-injection or PE overwrite techniques, and this is a case where the malicious payload is unpacked and then injected into the same process that the malware is spawned with. So there's no second process involved. Basically, they're just unpacking the payload and then transferring execution to it. So there's a couple different ways that this could happen. They could unpack the payload into memory somewhere and just transfer execution directly to it. That's common. Also, there is a way where they would basically unpack a DLL and then load the DLL into their own process and transfer execution to it. And then the third and probably most common way is a section overwrite, where they basically unpack a small stub of code into memory, transfer execution to it, then they change the permissions on the sections of the PE file of their process, and they write code into those sections and then transfer execution back to the sections in their PE file. And that's the type of injection that we're going to be talking about today. So we're going to talk about PE overwrite, and of course the most common packer that uses the PE overwrite technique is UPX, which probably most reverse engineers, that's the packer that they learned how to unpack first because it's so simple and ubiquitous. And with that, it's basically the same sort of idea as what we're seeing here, where they basically have a stub which basically unpacks or decrypts some code, writes that code into a section, and then transfers execution back to it. Now, what we're going to talk about today is something that's a little bit more advanced. It's not UPX. You can't use the UPX-D tool to unpack it statically, but it is kind of interesting, and it's worthwhile to know these techniques. And then there's actually a second stage to the malware we're looking at today, which does an unpack to DLL and then load DLL type self-injection. So we're basically going to cover both of those today. And the malware that I chose is something called Redaman. I'd never heard of it before. I just saw it analyzed on malwaretrafficanalysis.net, Brad's excellent blog. If you guys are looking for samples to analyze, definitely head over there and check out some of his work. It's awesome. You can see different traffic patterns for different malware, and he always uploads the samples so you can download them as password protected zip files. So it's a great resource to try and grab samples to take a look at. Now, I'd never heard of Redaman, and this tutorial is not going to analyze that malware at all. We're just going to unpack it. But the reason why I chose it is because it's kind of cool. It only does self-injection and has 2 stages, and the result is like it's good for this tutorial, but also it's kind of cool because if you run it in a sandbox, you can see here that it only has one process that's launched. So for those of us who do a lot of malware triage, you're kind of used to seeing a whole chain of processes with the same name. They keep on launching themselves and launch other tools and stuff. This one's kind of cool in that it only launches one process and it does all the work inside that process. So that's what we're going to take a look at today. So with that, let's pop over to our VM and get started. Okay, so I've popped over to my VM here, and it just has a few tools in here that we're going to use. Maybe PE Bear, which is a pretty cool tool from Hasher's Aid, x64 debug, and a hex editor. And if you guys are interested in setting up a similar VM, we have some instructions on our channel and also a blog post about how to set this up for free. You can get a temporary VM license from Microsoft, and we have a one-click installer that will install these tools for you guys if you're interested. So to get started with, since I know that this is going to be self-injection, as we just saw in the sandbox, there's only one process and it's malicious, so there's definitely gonna have to be some self-injection here. So that means that I'm going to have to focus on the allocation of memory and trying to figure out where they actually allocate the unpacked payload. So let's open up x64 debug here, and I'll show you how I go about doing this. So we'll just drop our sample over here. Now, like we saw in some of those diagrams where I talked about self-injection, the first thing we want to do is start monitoring all the allocations of virtual memory. So I'm going to put a breakpoint on the return from the virtual alloc call, and the reason why I put it on the return is because after memory has been allocated and you return from the API, the EAX register, so the return from that function, contains the address of the newly allocated virtual memory. So instead of putting a breakpoint on the beginning of the function, I put a breakpoint on the return. So let's just use Control G here to jump to virtual alloc. And then I'm going to follow these jump statements. So we're at the entry point here. Well, actually, kind of interesting. There's actually a redirect to virtual alloc. We've covered that in some other videos, but basically this is a shell, a wrapper around virtual alloc. So what we do is we sort of highlight this, press enter to jump into it. There's another jump here, and then we get into the kernel-based DLL that has the actual main code for virtual alloc. Just to cover it really quickly, kernel32.dll has a wrapper that's called virtual alloc that you call into, but inside that wrapper, they actually call into a DLL called kernel base, and that contains the actual code for virtual alloc. So that's what we've done. We've just jumped into the you can see up here, the kernel-based DLL, and we're going to put a breakpoint on the return here. So we're just going to press F2, add that breakpoint. And the second thing we want to do is put a breakpoint on virtual protect. And the reason for this is because if they're going to do some self-injection, they're going to inject code into their own process, they're probably going to have to change the protections of the memory segment so that they can actually run the code. And this is doubly so for PE overwrites. So if they're overwriting a section, generally if we look at the permissions of the section when it's loaded, it won't have write access, because why would you need to write to your own PE sections? That's obviously a trigger for any virus. Anytime you sort of see write access permissions on a PE section, it's probably going to be packed. So a lot of malware nowadays will actually load the sections non-writable, just like a normal PE, and then they'll use virtual protect to change the write permissions. So we're going to put a breakpoint on that as well. So I can just press Control G to go to it, virtual protect, jump to it, and we're going to put a breakpoint on the entry point to virtual protect, because in this case we actually just want to see what's passed into it. The first argument for virtual protect will be the address of the memory section that they're changing the protections of. So we'll just come in here, we can do a right click, toggle the breakpoint instead of F2. You know, why not mix it up, use a little bit of mouse, use a little bit of keyboard. So now that we have those two breakpoints set, we can probably actually start running this and seeing what happens. I'm going to just expand the window a bit here, give me a bit more room to work with. All right, so we'll just press run. We hit breakpoint on the entry point, which x64 debug always sets. So it's always going to set a breakpoint on the entry point for the PE file. So that's not really of interest to us. So let's continue running here. And we hit our breakpoint on return from virtual alloc. So just like I said, we can see in the EAX registers the newly allocated virtual memory. You can right click on this and follow and dump. And now, of course, we're showing the newly allocated memory down here in our dump. Now, what we're going to do is kind of a, this is a quick way to unpack, but it works like, 9 times out of 10, 10 times out of 10. Almost always this works. Basically, we're going to look to see what's written into these sections. We're going to look to see whether it's something of interest for us. So let's continue to run here. We can see they've written some stuff into it, and I'm curious, I think it might actually be some code, maybe a stub of some sort where they're going to actually do the unpacking in this code. And one trick here you can do is just right click on it and do follow in memory map, and you can see where it's been allocated here. So it's just a code segment. It's sitting outside of our PE file here, so it's just sitting up here. It's got execute read write privileges, so almost certainly they're going to jump into that and start executing. So not a big deal. It's kind of what we expected. That's probably their stub. And the reason why we stopped is we've hit another return from virtual alloc. So there's a second memory section that's been allocated here. So if we right click and follow and dump, we're now tracking 2 memory sections. So let's continue to execute here. We hit a virtual protect, which is kind of interesting. And we also see there is a PE file file that's been written in here. So there we go. Anytime you see a PE file written into a newly allocated memory section, it's probably a good idea to dump that out and take a look at it. So that's definitely what we're going to do here. So we're going to right click, we're going to follow a memory map here, and we're going to right click here, and we're going to dump to a file. And let's save it on our desktop here. So since that's a PE file, let's use PE Bear to take a look at it. So PE Bear, pretty awesome tool for quickly triaging PE files. We'll just drag this in here and let's take a look at the sections. So sections, everything looks pretty legit. And by that I mean, it doesn't look like there's anything too messed up here. It's got some imports, there's nothing wrong with it. And what I'm really looking for here is I'm looking to see whether this PE file is in its mapped format. So if it's actually being ready to be executed, or if it's in its unmapped format, which is the format that exists on disk. And the difference is if you look at the section headers here, in the unmapped format, these sections will start at the raw addresses, and in the map format, they will start at the virtual addresses. So sometimes if you dump a PE file from memory and it's in its map format, you'll actually have to edit this table to make the raw address align with the virtual address. Now in this case, it looks like we don't have to do that. Everything looks fine, imports look fine, so it looks like we've actually dumped out a legitimate exe file. Normally what I would do at this point is I'd actually kill the debugger, and I would maybe open up an IDA and see if there's any strings or anything like that. But what I'm going to do, because I've done a pass through this once before, is I actually want to show you one more thing here in the debugger so you can see what they're actually going to do with this file. So if we close up PE Bear here, remember we broke on virtual protect here. So why don't we look and see what they're trying to change the protections of. So on the stack here, there's the return, and then this is the first argument. So that's the memory section that they're going to change the protections of. And if we look at that, that's actually the memory section where if we look at the memory map here, where our PE file was loaded at. So they're actually going to change the memory protections of the PE file that was loaded for this process. So this looks to me very much like they're going to do a PE overwrite. And I'll probably walk you through one more step in the debugger. Again, we don't have to go through all this because we actually have the PE file we just dumped out from memory. So what they're going to do is they're actually just going to overwrite this PE file, the PE file that spawned this process. They're going to just overwrite it with the PE file that we just dumped out. So there's no need to actually walk through that because we have the payload already. But I do want to show you something kind of interesting. So if we go back to our CPU view here and we just run until we return from virtual protect, and then we step once to go back into the code, look at where this is pointing. So let's follow this in our memory map. So it's actually being executed from that little blob that we saw first injected into a memory section. So we were indeed correct. They've actually created this section here. They wrote some code into it, a loader stub. Then they used that code to unpack the payload, which we also found in memory. And then now they're changing the protections of the PE file because they're probably going to overwrite it. So kind of interesting. Again, I won't walk through the actual overwrite because it doesn't matter to us. We've already dumped out the payload. But the next step here is to take a look at that payload and see what's going on. Okay, so I've popped over to my other VM that I use to analyze malware with IDA, and I've opened up the dumped PE file in IDA Pro here. And when we open it up, I see a few things that are immediately, to me, this looks like another packed file. So the first thing is if we look at the top here, we can see the blue is a little bit of analyzed code, and then we have this giant bar of this kind of yellow I don't know what color this would really be, like some sort of ugly chartreuse, telling me that there's a lot of unanalyzed data here. Anytime I see this sort of thing in IDA's profiler here, it immediately tells me that there's something's wrong with this file. Also the fact there's hardly any functions, and in the imports, there's hardly any imports here. So it tells me this is probably packed. So let's take a closer look at it and we'll see if we can't figure out how it's packed. One of the ways to do this, I guess there's two ways. So first would be just to dive in, but one of the easy ways or a quick trick here would be to jump to the beginning of this blob here. So we just move the cursor over here. You can see it's in the data section and it has an XREF, it has a cross-reference. So if we just right click and jump to the cross-references here, sometimes you can actually see where it's being unpacked. And yeah, and we're lucky here. So we can see here's a rotate left and XOR loop that's using the, that points to this address. So if we just name this address blob1, so we can see we move that into EAX, and then we move what looks like maybe a length into ECX, which we're using to decrement this loop here. So that's probably the length of the blob here in hex. And what do we move into EDX here? We move, oh, it looks like this is the key. So it looks like they've moved a key into EDX. They're using that to XOR with bytes from the blob. They move through the blob byte by byte, and they do a little XOR and then a rotate left of the key. So this is standard, basic basic level, basic encryption. I can't say that word. So yeah, this is just basic XOR encryption. And so we've pretty much already identified how they're going to decrypt that blob. Let's look down here so we know it's been moved into EAX. Let's see what else they're doing here. So they allocate some memory. Oh, here's something interesting. So you can see a call to load library, which is used to load DLLs. And if we scroll down, I think, yeah, there's going to be a get process address too. So this is very common when somebody is going to do some dynamic API resolving. So we can see there's a bunch of bytes being pushed into this buffer here, and then that buffer is pushed as an argument to load library. So anytime you see this, this is what we would call stack strings. This looks like they're building a string byte by byte, and you can actually just hover over these bytes and press R and turn them into characters, so you can read what they are. So it looks like they're building the string ntdll.dll, they're passing that to load library, then the return from that is going to be pushed into get process address. So they're going to load something kind of funny. That's not get process address, that's get procedure address. Yeah, I for some reason it's always stuck in my mind to say process address. It's not, it's procedure address. Obviously they're not getting anything from the process, they're getting a procedure. So they're basically trying to find the address of an API, so a procedure, from ntdll.dll, and we can use our same trick here. This looks like another stack string, so we just press R and oh, this is interesting. So this is RTL decompress buffer, which is a API used to decompress stuff. So sort of like unzip. And so I think what they might actually be doing here, so EAX is the return from get proc address. So that's going to have the API address for RTL decompress buffer. So let's see where they move that. They move it into EDX and they call it here. So let's just put a RTL decompress buffer. And so that's what they're calling here. So for RTL decompress buffer, the first argument here is the type of compression algorithm that's used. The second argument is the buffer that's going to contain the decompressed data, then the size of the decompressed data, then the compressed data, the buffer that contains the compressed data, and the length of that compressed data. So ECX we saw here is actually blob1. So they're going to decompress it with RTL decompress buffer after they've decrypted it, and they're going to store it in this LP buffer address. So most likely this is going to be a PE file. Let's just follow this through a little bit. We can see what are they doing here. So they're doing a get temp file. So they're going to create a path to a temporary file, and then there's probably going to be a create file. Yeah, so there's a create file here. So they're going to actually create that temp file, and then they're going to write to the file. And what do they write to it? They're going to write the buffer that they just decompressed. Okay, so they're going to use that XOR decryption routine to decrypt this buffer. Then they're going to use RTL decompress buffer to decompress it. Then they're going to create a temp file and they're going to write it to the temp file. Now, what are they going to do next here? I have a sneaking suspicion they might actually, this might be a very old trick. So they are going to take the temp file, move it into EX, push EX as argument to load library. So they're going to then load that temp file as a DLL into this process, and then probably they're going to pass execution to it. What's this get proc address here? Where is the library? Okay, so they're going to load that temp file as a DLL, and then they're going to get a proc address. So they're going to get the address of one of the exports for that DLL. And what is the export name that they're going to get? Something called DLL get class object. Okay, well, I guess maybe the DLL, the unpack DLL, is going to have an export called DLL get class object, which they're going to get the address for, which is coming back in EAX, and then they're going to call it down here. So we're going to call this jump to unpacked and loaded DLL. Okay, and so what are they going to do? They're going to push this as an argument to that call. So let's see what they're pushing. Let's see if this is of any interest to us. I don't know, I'd have to probably analyze the malware to figure out what this is. But they're going to push host space then a bunch of zeros as an argument to that DLL when they call into it, and then they just exit. So that's all there is to this packer. This is something that's really not used very often anymore, because in order for them to unpack the sample, they have to actually write the sample to disk unpacked. And of course, with modern antivirus, if you write an unpacked sample to disk, they're automatically going to check it. So this is actually a pretty archaic way of unpacking stuff. You don't don't see too often. And it's also one of the reasons why I wanted to cover it, because I think it's kind of cool. I want to learn a little bit of the history of how packers used to work. So there's two ways now to proceed. Basically, we could try and write our own little Python algorithm to do the decryption. Then we could find out what the decompression algorithm is that's used, and we could decompress it using a tool. Or we could take the lazy way, because we know they're actually going to write the unpacked DLL to disk. We just open up our debugger again, run through this, put a breakpoint on the load library, and find out where the unpacked DLL is written, and just grab that. So why don't we hop over to our debugger again, and we'll see if we can't unpack this real quick. Okay, so we're back in our debugger here. I'm just going to rename this dump with an exe extension on the end of it. Now you don't have to do that. I just do it because I think it's a little bit cleaner, but you don't need to, because if you load it in x64 debug, it'll actually just automatically load it as a PE, so you don't need to. But again, I just think it's cleaner. So let's open up x64 debug here, drag in our file. So like we saw in IDA, you want to add a breakpoint on load library, because then you can see where they've dumped the DLL to disk, what the temp file path is. But if you add a breakpoint on load library right now before the exe is fully initialized, you're probably going to end up loading a bunch of other DLLs that are needed for execution. So what I like to do is just run until we hit the entry point for the exe. So we've hit the entry point here, and now we can add a breakpoint on load library. So let's just come in here, we'll press Control G, we'll do a load library. And we're going to go load library W, because there are two versions of Windows API calls that take in a string argument. So any Windows API call that takes in a string argument is going to have two versions of itself. It's going to have an A and a W. A stands for ASCII and W stands for wide string. The A calls are actually just wrappers. All they do is transform all the string arguments into wide strings, and then they call the W argument. So we always just put breakpoints on W's because they're always going to be called, whereas the A's may not always be called. So let's put a breakpoint on it. So we just jump to it here, going to F2 to put a breakpoint on it, and now we can run and see when it's hit. So it's being hit immediately because, again, there's almost no code in this packer, and we can see the first argument to load library is the path to the DLL that's being loaded, and in this case it is a temp file. And let's just expand this a little bit so we can see it. Temp folder ee54.tmp. So if we open up our browser here, we go into the temp %tmp, and we're not going to see it there because probably what they've done is they've hidden it. So here's kind of a trick. If you can't see it in the file browser, but we know it exists obviously because we can see it here, what you can do is you can open up a command shell and browse into that directory. So cd into %temp, and then in %temp, where you know the file exists, you can use the attrib command, attrib. And it's going to list all files that have special attributes. So in this case, we can see the EE54 temp file has been set as a system file, it's hidden, and it's an archive file. So we can actually use the attrib command to remove those attributes, so we can actually see it in our file browser here. So we just do attrib minus hidden minus system, and then the path to it here, which is ee54.tmp. And now if we look here, it's showed up because those attributes have been removed. So again, if you know there's a file that exists that's been dropped by malware in a directory, can't really rely on the file browser to find it, because of course it might be hidden and set as a system file, so you can't change the hidden attribute. So what you have to do is use those attrib commands. Of course, there's lots of other like sysinternals tools which will just list all files. So, if you're doing real incident response, you'd probably use those. But in a pinch, attrib works just fine. So now that we have that file, we can actually just open it up in our PE bear here and take a look and see what it is. So we open it up here. So everything's looking pretty normal here. If we go to our section headers, everything looks pretty normal here. And if we look at our imports, it has some imports. Yeah, pretty decent amount of imports. So it's probably unpacked now. If you look at the discrepancy between the size of the raw text section and the virtual text section, you can see the virtual text section is quite a bit larger than the raw one. That's telling me that probably, so again, you can look at the comparison here. So you can see the raw text section is very small, but when it's mapped, you can see it's very large. So that's telling me that there's probably going to be some monkey business going on when you load that file. But again, we know what arguments they're loading it with because we saw in IDA, we saw the export that they were calling, and we can obviously check here to see in the exports, do they have that export that we saw? And of course, they have it right here, DLL get class object. So we've now unpacked this file, and that's that's pretty much all there is to it. Now, unfortunately with this malware, like I said, the unpacked file, so this is actually unpacked, there is some extra stuff going on with it that's kind of tricky. If you load it up, you'll see there are no strings in it, and there's a bunch of other like hidden stuff. So it isn't super clean to load an IDA and just see what's going on. You're gonna have to do some extra work, but we're not gonna cover that in this video because I only want to cover the self-injection part of it. However, if anyone's interested in taking a look at this malware, I think it looks kind of interesting. It looks like something that might be kind of cool. You can see they actually use crypto domains to resolve their C2s, and there's some fancy stuff in there. I think it's kind of cool. If anyone's interested to take a look at it, you guys can hit me up on Twitter or whatever with your analysis. I'd love to see what you guys do. But that does wrap up the unpacking part for this tutorial. So basically 2 types of injection. One is a PE section overwrite, where we kind of circumvented that by dumping the PE file out of a buffer before they even had a chance to write it into the sections. So it was a clean dump. And the second part was a DLL that was unpacked and written to disk, which we then just went and collected. So if you ever come across a piece of malware where you know it's malicious and you know it's packed, but you only see it's running one process, there's no extra processes being spawned, this is the way you would attack it. You would basically put those breakpoints on virtual alloc, virtual protect. You would look for what was being injected, see if you can spot a PE file, dump it out, take a look at an IDA, see if you have to do a second stage. So that's pretty much the process they use. And like I say, it works, pretty much 9 times out of 10, probably more often than that. It's pretty rare that you see a self-injection that doesn't use one of these techniques. So hopefully that was interesting, and hopefully you find it useful as you guys are going through and looking at malware. Also, a huge thanks to Fabian for doing this collab with us and supporting our channel. Obviously, we're huge fans of LiveOverflow over at OALabs. So a real treat to be able to sort of collab with him. So hopefully you guys enjoyed it. And until next time, keep exposing the mechanics behind the malware and stay curious.